Today we're going to talk about lesson 8.2.2 complex roots. Yesterday we talked about imaginary numbers coming from the square root of a negative. We talked about complex numbers. That would be numbers that have a real component and an imaginary component. Today we're going to continue talking about that stuff and talk about complex roots. Now remember, other words for roots are solutions, zeros. We used to think of them as x-intercepts, but x-intercepts are only for real roots. We know sometimes an equation or a graph will never hit the x-axis, and we just learned yesterday that that doesn't necessarily mean it has no solutions. It just means that it has no real solutions. Okay? So if I want to find the roots or the solutions, instead of y, I'm going to put a 0 here. Okay? And then I'm going to proceed to solve from there. I know some of you are going to want to multiply this out and then use the quadratic formula or try and factor. However, if it's already in graphing form, let's just use the undo method. Okay, so the first thing, the easiest thing to undo is to subtract 9 from both sides. The second thing we can do to undo is take the square root of both sides so we can get rid of the squared. Now remember, anytime we take the square root of something squared, the result is positive or negative, the square root of whatever this is. So on the right side, we get x plus 5. On the left side, we learned yesterday that the square root of negative 9 is the square root of 9, and the square root of a negative is I. Okay, so the square root of negative 9 is 3i. Can't forget about the plus or the minus. Okay, solving for x, I'm going to subtract 5 on both sides. Remember, we always write the real component first and the imaginary component second when we're talking about complex numbers or complex roots. Okay, so we have solved the equation. We have two solutions. One is negative 5 plus 3i. The other one is negative 5 minus 3i. This is how we usually write it, but we just need to keep in mind this is two solutions. Okay, number 8-79 part B. Again, it's asking us to find the roots. I've already put the 0 in for you. In the book it has y equals. Now this one, we could complete the square and solve using the undo method like we did part A, or I know you guys love the quadratic formula, so let's do that. Okay, quadratic formula, negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And if we simplify, 16 minus 36, that will give us a negative 20 inside the square root. Okay, and again, before yesterday, we would have stopped and we would have said no real solution. But yesterday we learned if we have a negative, it's going to pop out, it's going to become imaginary. We know that 20 is really the square root of 4 times the square root of 5. So I'm going to have 4 plus or minus. Square root of 4 is 2. We've got the negative I. And then square root of 5, I can't simplify any further. All over 2. Okay, but we never leave an imaginary, or I'm sorry, a complex number in this form. Okay, we have to divide out the 2. Even if it was a number that doesn't divide nicely or evenly, we still separate it into a real and an imaginary component. So 4 divided by 2 is 2. Remember, when you're dividing things that are outside and inside a square root, the outside parts divide with the outside parts. So 2 divided by 2, that disappears, and we just get I root 5. So my two solutions, they are complex solutions or complex roots, are 2 plus I root 5 and 2 minus I root 5. Those are my two solutions. Okay? So let's take a look real quick at what our two solutions in each problem looked like. Okay, so this was part A, this was part B. Question number 80 asks us to see what do we notice about these. And hopefully we're noticing that in both equations we came up with two complex roots. Okay, so we didn't come up with one complex and one real. Remember, complex roots always come in pairs, okay? And also you'll notice that the roots for each equation are the same except for the middle sign. The roots are the same except for the middle sign. So we learned yesterday that when two things are the same, I guess I could have left this right here, except for the middle sign, we call those complex conjugates. That's just a vocabulary word, and that you're going to see a little bit why that becomes important today. Okay? So in question number 81, there's quite a few parts to this. Question number 81 is going to ask us over and over to find the sum and the product of these two complex numbers. Okay? Let's make the sum be so easy. So easy. Okay? 2 plus I plus 2 minus I. We're just adding. Remember, when we're doing operations with i's, we can really think of them as any other variable until we get to a place where we maybe have to simplify an exponent down. Okay? If we're simply adding, we're combining like terms. 2 plus 2 is 4. Positive I plus negative I is 0. The sum is 4. Okay? The product is a little bit more complicated. Okay? We can use our generic rectangle. You don't have to. We'll put 2 plus I, P for product, and 2 minus I. And as we multiply through, we get a positive 4. We get a positive 2I. We get a negative 2I. And up here we get a negative I squared. Okay? You should notice right away the positive 2I, the negative 2I make a 0 pair. They're gone. As we remember from yesterday, I squared really equals negative 1. So this is negative 1. Negative is positive. 4 plus 1 is 5. Okay? So the product of 2 plus I and 2 minus I is 5. Okay? There's quite a few more of these for you to do, B, C, and D. Okay? So I want you to try. I want you to find the sum and the product. Go ahead and pause the video, find the sum and the product of each. Same thing for part D. Okay? Pause the video, you try it. When you're done trying it, come back, fast forward me, see if you get the same thing. Part D, I'm going to talk through this one just a little bit more. By now you've figured out that the sum is real easy because you're adding the real parts and the imaginary parts cancel out. The product for this one, some of you are going to be able to do this in your head and that's just fine. If not, let's take a look at what this looks like together. So I have a 1 and I have a positive I root 3. And I have a 1 and I have a negative I root 3. Notice when I do my generic rectangles, I just put my stuff wherever I have space. I don't really stay consistent. Okay, so 1 times 1 is 1, easy. 1 times I root 3, also easy. 1 times negative I root 3, no problem. Okay, now here's where it gets a little bit weird. A negative times a positive is a negative. I times I squared, square root of 3 times square root of 3 is 3. Okay, so let's see what happens here. These corners, I root 3 and negative I root 3, they make a 0 pair, so they're gone. Okay, what's remaining are these two boxes. So I have this one, and then I have this stuff. I have a negative, I have the 3, and remember, I squared is a negative 1. So negative times negative is a positive, 1 times 3 is 3. So I have a 1 here, I have a 3 here, so the product is 4. Okay? In part E of this question, it says, okay, you've done these enough that now you should be able to look at this and say 3 plus 2I times what will give you a real solution? What makes the imaginary parts just disappear? And hopefully you have noticed that all of those examples in A, B, C, and D all were complex conjugates of each other. They were exactly the same except for that middle sign. So in order to get a real number, you have to use complex conjugates. Okay? Now, when you multiply two complex numbers together, do you always get a real number? And they gave you this example to check it out. Okay, again, generic rectangle. Ooh, I'm out of space. -4 plus 5i, -4 plus 3i. I get a positive 16, -12i, -20i, 15i squared. Okay, this time these corners do not cross out. They just combine as like terms. So I have 16, I have -32i, and then I have 15i squared. Again, I squared really represents a -1. 15 times -1 is really a -15. So again, when I combine like terms, 16 minus 15 is 1, minus 32i. So the question was, when I multiply two conjugates together, do I always get a real number? And the answer we have found is no. We get a real number when we multiply the two conjugates together. Okay? Part G is the same thing. It is asking us to say, well, what if it's just some variables here or parameters? If we have a plus bi, what should we multiply that by in order to make sure that we have a real number? And again, just like we talked about yesterday, it's the complex conjugate. The reason we even care about a conjugate is so we can multiply them together to get a real number. Okay? Now, at this time, what I want you guys to do is question 8-82 from your book. And the question asks you to go back to A, B, C, and D of 8-81, okay, all four of these, and you're going to figure out what could have been the quadratic equation, so y equals ax squared plus bx plus c, that created these two things as roots. Okay, what quadratic equation can you write that would have come up with two solutions of these? Think about that for a few minutes. If you're stuck, go ahead and look at the guided practice or the further guidance section, which is 8-83, 84, and 85. Take some time to go through and answer question 82 using further guidance as necessary. Then check back in with me on my next video.